Okay, good morning everybody. We were looking at this simple example where we had a heat source in a pipe which was located at some location, and we looked at the heat source having a unsteady fluctuation, and we modeled unsteady fluctuation in terms of the velocity fluctuations using the so called Crocos n-tau model. This is a very famous classical model, and then we try to find the stability of the system. So just to recap, this is the pipe with length L, and yes, please ask me. Okay, there is a pipe with length L, and somewhere in the pipe we have in the duct we have kept a heat source. So there is a flame holder and a flame is there, and you have region 1 and region 2. Region 1 is cold, region 2 is hot, and they can have different temperatures, and it is a premixed fuel, and they are coming here, burning right here and coming out. So we have a closed end here and an open end here, and we wrote the solution in terms of this A and B, the left running and right running wave on the left side, and the left running wave and the right running wave on the right side. And what we did was to apply a boundary condition here that velocity is 0, applied the boundary condition that pressure is 0 here. This is the same manner in which we did a quarter wave tube, but then we did something extra, that is at this flame we applied the jump condition that is pressure is continuous but velocity jumps, and then we got 4 equations and 4 unknowns, in 5 unknowns. We got 4 equations and 5 unknowns, and we discussed why this is okay. Why was that? Anybody remember? Yeah, so one is the omega itself we are solving for. So we have eigenvalue problem and get a dispersion relation to solve for eigenvalue, that is fine. And then we get the amplitudes, then we are left with 4 coefficients and 3 equations. So why is that okay? Yeah, we are having a linear problem, so we cannot really solve for the amplitude. All we can get is we have 4 wave amplitudes, we can get 3 in terms of another one or something like that. And then if you put the determinant of this matrix to be 0, we can actually get the relation for the omega, which is complex, and the real part indicates the periodic quantity and the imaginary part indicates the growth rate or decay. And we had a relationship of the form multiplied by 1 plus n equal. I hope you checked this at home. I checked my calculation again, it seems right. And now in McManus paper there is a slight difference. Anybody notice the difference? There he uses e power minus I omega t. I am using e power I omega t. I generally like it that way for no reason. You can do whichever way you like, and therefore some of the in between results will be different. So after this we made a bunch of approximations. This equation can be solved numerically, but we wanted to get some relationship analytically so that we can see and feel pleased about the relationship, and then we can look at the equation, smile at the relations and understand some things. But then you have to do a lot of simplifications. So we made the simplifications that ρ1 equal to ρ2, C1 equal to C2 and so on. That means we are kind of assuming an average temperature in the duct which is constant, and then we get a solution of the form so K1 equal to K2 equal to K, and we are also assuming that the flame is at the middle of the duct. Then things really become simple. So A will be equal to L over 2 if the flame is at the middle of the duct. It is not like the flame has to be kept at the middle of the duct, you can keep it anywhere, we can get simple answer because the trigonometric functions can be simplified easily. And so we derived this relation. I hope you checked it. I think this is okay. And when n is much less than 1, we can get cos 2k. So this is quite simple that we can now play with it. So the idea is, assuming that we know n and tau, what should we calculate? Omega. And in that we have two parts, one is the periodic part, the frequency, and one is the growth rate, decay rate. That is our objective. And if you are having growth rate, we say it is unstable. If you are having a decay rate, we say it is stable. So we can do this in 2 steps. This is again similar to one of the problems we did earlier, where I looked at a small admittance and then I compared it with a open tube or something like that. That was a problem we did. So it is similar to this. So first let us study the case without combustion. So if you have a general result, then we should be able to derive our earlier known results from it, right. So let us say n equal to 0. This would mean no heat release, no oscillatory heat release. Now I must say that when the temperature jump is 4, you can also get a closed form solution, and I would give it as a homework to work it out. Okay. So now n equal to 0 would mean no oscillatory heat release. So what happened to this relationship? Cos of 2k equal to 0. What would that mean? 2k is equal to cos of what? Pi by 2 is 0, then 3 pi by 2 is 0, and so on. Pi by 2, 3 pi over 2, 5 pi over 2, etc. We look at the fundamental, and let us see. K is, so let us call this as k naught, because it corresponds to n equal to 0. So 2 times omega naught over C A, which is 2 F naught over C into A equal to pi over 2, which will mean F naught equal to, let us cancel this pi's, this is 4. Is this okay? Should we have 4 or 8 here? It's 8 because 2a is L, so we can rewrite it as C by 4L. So the other ones you can get it as corresponding to 3 pi by 2, 5 pi by 2 you will get 3c by 4L, 5c by 4L, and so on. So you can just check to ensure. So if you have this real omega or real frequency, what happens to the growth rate? There is no growth rate or decay rate. But let us say in the presence of combustion we have a departure from the solution and we express the new solution in terms of the solution, then maybe things may be easier. So we will say k equal to k naught plus k prime in the presence of oscillatory heat release rate. And we say that n is very small and k prime is very small. So now we can expand the solution. It will be cos of this can be written as cos 2k naught cos 2 k prime a minus sin Now, can you simplify it any further? So, cos 2 k naught a would be 0, right? That would be the case when there is no heat release, and we are expanding around that. So, we can drop this term, and what will happen to this term? 1, perfect. So, we would have this thing as just a minus 1. Yeah, I am doing first mode for k naught. I mean pi by, like if you have look for 3 pi by 2, you will get f1, f2 will be phi c by 4l, and we can work out. I will give the 3/4 mode as a homework. I will work out quarter mode and we will give the 3/4 mode as homework. But what about the sign? You said minus? This is okay. So, if k prime a is very small, we can even call it sin theta as theta. So this would be minus k prime a. You can actually do without all these approximations, no problem, but with the approximation you can get some simple results which you may appreciate. That is the idea, at least I appreciate. So if you look at this, so if you expand this, this will be, we had this relation for k as cos 2k equal to half n e power minus I omega tau. Again this is for the case of n is really n being really small. This is half cos I omega tau minus I sin omega tau. So when you have a complex equation, you actually have two equations, one for the real part, one for the imaginary part. So we can say k prime real is minus 1 over 4 n over a cos omega naught tau, and I hope I have the signs correctly. Please let me know if I made a mistake in the signs. Signs are quite critical, otherwise if there is a sign change, what you calculate as growth rate will be actually decay rate. So this k prime is actually departure of the wave number from this natural modes, the wave number corresponding to natural modes, okay, and we are saying that the departure is small. So now the natural mode has no growth rate or decay rate, it is 0. So if you look at the k prime imaginary, from that we should be able to tell if there is growth or not, right. So what are the conditions for the instability to occur? That is what we are interested in. So if I write this equation, which I wrote n number, which I wrote so many times, I omega real times I omega imaginary t, this is equal to e power I omega real t times e power minus omega imaginary t. So, if omega imaginary is negative, we will have growth, right. So, instabilities to occur, we need omega imaginary to be negative. So, this is the condition for instabilities to occur. So, that is good. So, that is our main result. We should mean n over 4a sin omega naught tau should be less than 0, or sin omega naught tau itself should be less than 0. That would mean that minus pi less than omega naught. This would be the quadrant in which a sine is positive from 0 to 180 degree, from 180 degree to 360 degree sine is negative. So, that is what I have written, but there is always the ambiguity of some 2j pi or something like that, of 2 pi or 4 pi or 6 pi. I can rewrite omega in terms of time period, so that you can get a ratio of tau over t. So, you can multiply by tau naught and remove 2 pi, you will get this would be the condition you would get for instability. So, for certain time delay within this which satisfies this relation, if this occurs, you can have the fundamental mode to be driven, the quarter wave mode to be driven. So, it does not have to be that delay has to be small, the delay can be more than a period and then it can come in a range where it will drive, that is also possible, okay, and delays need not be short also. So, this is the condition for instability, and if your delay is outside this range, if it does not satisfy this inequality, then you actually have decay or it will not be driving. Now, the actual, see, we have not included damping in our model as was pointed out in last class. So, the actual regime will be smaller where you get instability, because damping always helps to make the thing stable, the system stable. So, your stability regime will be instability regime will be smaller, and if the damping is really a lot, there will be no instability at all. So, the next question I would have is, so we derived some condition for stability, but we also earlier mentioned derived something on the energy, like a new energy corollary, which had a term which can be driving or damping depending on the phase between heat release and pressure and so on. So, and this was called Rayleigh criteria. According to that, if the heat release rate was in phase with the acoustic pressure, we said we are going to have driving, and if it was out of phase with the pressure, we were going to have damping. So, Rayleigh criteria is often used to quantify or to look at combustion stability studies, and we actually use this to quantify the coupling between heat release and the acoustic pressure fields or unsteady heat release and the acoustic pressure fields. And the criteria says that if the heat release rate is in phase with the pressure, the acoustic field will be amplified. Now we can imagine that the heat release rate may happen over a finite zone, we did have a lot of discussions on this earlier. So in that case we do not look at it as an integral thing. At each point you will have a different pressure, you can have a different heat release rate, but if the heat release rate is locally in phase, then at that point the wave is being amplified. At some other point it may be out of phase, it may be decaying. So the net effect is what drives the system or damps the system, but locally it can vary. So people define something called Rayleigh Index, which is used to quantify the coupling between acoustic wave and the combustion process, and it is a local thing. And T here is the time period of the oscillation. So if G of x, I mean having this x dependency says that it is a local thing, it acknowledges the fact that some place heat release can be in phase, some other place it can be out of phase. So if G of x is greater than 0, we say local amplification, and G of x is less than 0, we say local absorption or decay, or local damping, let us say. So we saw that if you look at the specific frequency, we have to have phi between pi by 2 and minus pi by 2. I hope it is clear how we got it, right? Should I do it again? I cannot read the expression. So we have P prime as cos omega t, Q prime as Q hat cos omega t plus phi. So our G would be 1 over t integral 0 to t P prime Q prime cos omega t times cos omega t plus phi. This we can use a trigonometric identity and say cos A plus B would be cos 2 omega t plus phi plus cos A minus B would be cos phi divided by 2 dt, and this is a periodic quantity, so that will drop and you will have only this. So this will say P hat Q hat, and the t will cancel, so over 2 cos phi. So if cos phi is positive, you will have driving, acoustic driving. If cos phi is negative, you will have damping. So positive phi will come when so this is, so it depends on the sign of this. So cos phi is greater than 0 implies phi is like minus 90 or pi by 2 less than phi less than pi by 2 plus, so minus uncertainty of 2 pi or n times 2 pi, which I cannot use n is already in the interaction, j times 2 pi or j times 360 degree. So we have to see if this criteria is consistent with whatever we got for our growth rate and decay rate, that is the idea. So we can check for consistency or correctness of the criteria that we derive, is that okay? So we cannot do it straight away because what we have is a relationship for heat release in terms of velocity, but that is not, it is not the phase. Rayleigh did not say that it is the phase between heat release and velocity, that is mattering. He said it is the heat release between, it is the phase between the heat release rate and the acoustic pressure. So that means you have to find the phase between pressure and velocity, which depends on the local acoustics. Okay, what is the quantity which indicates the phase between pressure and, or what are the factors that affect? Let's go back to, it's a very good question. So we'll answer this based on, try to look at recall what we did for this admittance and so on. So when you have a perfect example like closed and open end, we got always the phase difference between pressure and velocity as 90 degree, pi by 2. But if you have a left turning wave and right turning wave, you always got it as 0 degree or 180 degree, right. One case it is for the right turning wave pressure was P prime over rho c, for the left turning wave it was minus P prime by rho c. So if you have a travelling wave, then you would not get 90 degree at all, because it is energy flow. So there will be admittance, and admittance times P prime squared shows the power flow, admittance times P prime squared times area shows the power. So as long as the power is flowing, then you would not get 90 degree, and you will have one or something in between, and so on. So and the direction depends on which direction the power is flowing. So yeah, I mean you won't, it is not necessary that you have it at all 90 degree, but except in the case of a perfect terminations, then it is possible, like completely open or completely closed kind of terminations. Is that clear? Yeah, so this is the local acoustics which decides the phase between heat release and the velocity. Okay, it is the acoustic field in the duct, and so it critically depends on, so that gives the idea that, for example, if I found system to be unstable for a given boundary conditions, I can alter the boundary condition and the same with the same tau time delay and all that, the system may become stable, which is actually the principle for active control, which we will see soon. Okay, so if we can some way adjust the phase between pressure and velocity, then I think we can solve the problem, make any system stable, which is the clue towards this active control or anti-sound and so on. Very good question. Any other questions? Okay, so we need to look at the expression for pressure and velocity at x equal to a, which is the place where the flame is, right. So what was this? So what is the value from our, didn't come to last class. So this is the pressure at this location. Now what we need is heat release rate, which depends on the velocity at this location, but delayed by time tau. Okay, so what will be n times, it will be right, the rho c and all will get cancelled with those factors with n. Okay, it's, I will just say proportional, there is some constant there, the gamma minus 1 factor is there, so I strictly say proportional, and u is this. Okay, so we put the n, and time delay tau is like e power minus I omega tau, that is okay, right. So we need a relation between a and b, that's the only thing that is stopping us from calculating the phase between p prime and q prime. So we are saying that the solution is a small departure from the quarter wave tube, so we can use the quarter wave frequency into the boundary condition and see, we will get an approximate relationship between a and b, and then we will plug that in here. So our relationship was cos 2 k naught a equal to 0 or k naught a equal to pi over 4. So this was the boundary condition at x equal to 0, right, velocity is 0. So what we will do, we can use anything, but we need a relation between A and B, so it is good to have a relation which we have just A and B. So this can be written as A into cos pi by 4 minus I sin pi by 4 minus B into cos pi by 4 plus I sin pi by 4 equal to 0. So A times 1 over root 2 minus I over root 2 equal to B times or A over B equal to 1 plus I by 1 minus I. If I multiply top and bottom by 1 plus I equal to bottom will be is 1 minus I, so it will be 2, right, and this will be 1 plus I squared plus 2I, and this will go, so I will get I minus I, sorry,
A e power minus Ka.
Yeah, this is E for minus Ik, sorry, missed it, and that is what translates to is minus I. So we can see P at x equal to 0 comma t is, we can substitute for A as Bi, so A equals Bi, so you will get 1 plus I times B I omega t. Q prime goes like, so there will be some constant, some factor of gamma minus 1, I will not write that, n times I minus 1 B e power I omega t minus tau. Substitute A as IB and you can get this. So let us rewrite this as n times I minus 1. So we have to get the same factor here, only then we can write the phase here as the direct value. E power minus I pi over 2 is cos pi by 2 minus I sin pi by 2, which is minus I. So if this will be like equal to equal multiplying by minus I, so I minus 1 times I would be minus 1 plus I. So we can write this as, this is equal to n into 1 plus I times B times e power I omega t minus tau plus I pi over 2. So you have, here is the expression for pressure and here is the expression for, so Q prime goes like, so the phase is minus omega tau plus I pi by 2. So this should be between minus pi by 2 to plus pi by 2. Or plus 2j pi here. So this would give, what would give? Pi plus 2j minus n minus is this okay? So so this, if I multiply by minus 1, the signs will swap. So this should give, I can write omega as 2 pi f over t, sorry 2 pi over t, and if I divide throughout by 2 pi, I will get less than pi is gone. So in reality there will be multiple, okay, I'll pause. Okay, in reality it is possible that the multiple modes can be present, you do not know which one will come, and you can also have the individually you can have the you need not get the fundamental mode, you can get the 3/4 mode as somebody pointed out. So the next thing is we can actually analyze that also. So if you look at the next mode, so you will get 2k1 a equal to 0, which will give k1 a equal to 3 pi over 4, and this would eventually get, you get lambda equal to 8a over 3 or 4l over 3, or L is like 3 lambda over 4. So this is the three-quarter mode. So the homework is to determine the stability of the three-quarter mode. So if you do this problem and look at the region of stability, and you will find that there is a problem, because one would wish the time delays that create instability in the, suppose you have instability in the first mode and then you change the time delay to something else, and there is actually a region where the first mode is stable but the second mode is unstable. So you do something and make the first mode stable and you have altered the time delay. So now the first mode is quiet but the second mode might come up, and this is very similar to a life when we solve one problem, whatever we did to solve that problem will create a new problem. So I think it is like, if I have to do, I have to have a living, I borrow money from the bank and do business, but then eventually the bank takes away all my stuff because I can't pay back the bank or something like that. So you do something to, bad example, you do something to eliminate one problem, but then that very thing creates another problem. So that is quite possible. There is a overlap of overlap region where you have, there is a possibility that the first mode can be stable, but then you make the second mode unstable, and then there is even more complicated things which we will come to. But what is interesting is, now if you go back to this, and everything dependent on the phase that is coming out because of the relationship between A and B, and we got A was Bi, and this critically affected the phase. So can we do something to alter this end condition? So instead of having a hard wall, can we put a loudspeaker there and adjust the phase between pressure and velocity such that you can actually make the system stable. So you alter the stability conditions, and at whatever condition you want to operate, you want to make it stable. So that is the basis of active control. We will look at that in the next class. But what it involves is, we have to put some loudspeaker, and what phase should you put, we do not know, right. So we have to measure the acoustic field from the using a microphone, whatever is the acoustic pressure at some place, and then you have to find the appropriate phase that you have to put for the or the appropriate boundary condition you have to put, so that the acoustic field dies down. So this is the principle for active control. You might have, some of you may have Bose speakers, would know how it cancels the sound. So what it involves is, so in the combustor you put a piezoelectric transducer or a microphone, measure the sound, then amplify it and appropriately phase shift it, and use a actuator, which can be a simple actuator is a loudspeaker, or a piston complicated actuator can be a secondary fuel injection or mass addition or something like that. And then in the end you want to try to drive the system to stability. So we will look at that in the next class. So in summary, given a heat release model, we can calculate whether you have stable system or unstable system. Now how to derive this n and how to derive the tau, that is the crux of the modeling of the unsteady heat release rate, that we are not addressed. We said that it is a given thing, and in reality your model may be much more complicated than that. There may be other unsteady processes such as hydrodynamic instabilities, and under that you may not get the resonance frequency of the pipe as the, or you may not get close to the resonance frequency of the pipe, and the actual system may be highly nonlinear, and we will have to account for all that. But nevertheless, it is like the professor looking under the lamppost for the ring. So you looked somewhere and found a solution, tractable solution, that was the objective, and it illustrated something, that is there is some time delays under which you can get stability and so on. So I will stop here.